Hi, in this video I will be presenting some of the results which I found when benchmarking machine learning systems for their inference performance. So in this video I will be covering an overview of the experiment itself, the process to convert a model, some of the results I found when benchmarking, and then a discussion of these results. So in this experiment what we are doing is we're taking a raw tensor. So a raw tensor is a random tensor of data, and we are generating it using this command over here, np.random.rand, and then the shape of the tensor is the width, the height, and then the depth. So since it's a color tensor or color image, it has 3 channels, and n is the batch size. So we are going to pass this random tensor through the network, and we're going to see how long it takes for the network to infer this and give us an output, and from there we can time exactly how long it takes each operation of the machine learning pipeline. So the reason for doing that is because loading an image from a dataset actually results in similar results. Once the dataset is loaded to memory, the inference is exactly the same if you are using a random tensor, if you're using a real image. We're using the LaneNet model. This is a model which we found on GitHub, and it is a good starting point from where we can compare the results across a variety of systems. So we have actually split the benchmarking into FP16, which is floating point 16, and FP32, which is floating point 32 models for each device. Since we're only using NVIDIA devices, we are only taking TensorRT models because TensorRT is NVIDIA's proprietary model optimized format for the GPUs. We're using synchronous CUDA execution, and we're measuring the times for each line of code using a tool called Line Profiler, and we have tested batch sizes of 1, 10, and 100. So this is the model conversion procedure. For the LaneNet model, we have a frozen checkpoint, so it's a .ckpt file. So this is a frozen checkpoint file, and using some scripts we can change this to a frozen model file with a .pb extension. Then there's a tool called tf2ONNX which converts this to the ML exchange format called ONNX, which can be used for converting it to several other formats. And then using some NVIDIA scripts, we can convert this to a TRT file. And a TRT file is only for that particular NVIDIA GPU. So for example, a TRT file which I have developed for the Jetson will not work on my laptop, for example, because the TRT engine file is very device specific and it has optimizations for that device. So these are some of the devices which were tested. First is a recent gaming laptop with an RTX 2060 GPU and a powerful CPU. Then a 2016 Ultrabook without a dedicated GPU, but it has the Intel HD integrated graphics, and it has a low power, ultra low voltage CPU. Then we have the Xavier NX, which was tested in mode 0, which means it only uses 2 cores at 1.9 gigahertz, and it has the NVIDIA Volta GPU and 8 GB of RAM. And then finally we have also tested on the Jetson Nano as a form of a baseline, because this has 4 cores, so it has 4 ARM A57 cores at 1.4 gigahertz, and it has a 128 core Maxwell GPU with 4 GB of RAM. This is a typo, my bad. So the other thing which I've done is synchronous inference. So in synchronous inference, the main difference is that we are executing that line when we are actually running it. So the difference is in asynchronous, you will actually require a call to CUDA.synchronize, which will actually execute the operation. But in this case, since you want to time each step of the process, we use synchronous inference because that will allow us to time exactly how long each of these steps take. So that is useful because then we can find out exactly how long the inference time takes as well. And I'll just go through these lines. So the first line is reshaping the tensor, because TensorRT requires a flat tensor. So it basically requires the width, the tensor, the random tensor to be flattened to a vector. So that's why we have to do input.reshape -1. Then we need to copy that input to the GPU. So H to D stands for host to device. So from the system memory to GPU memory, we need to do a CUDA.mem copy for all the inputs, and after that we need to execute it. So this is where the inference actually happens in this line of code over here, self.context.execute. And then after that, in the next line of code, this is used for copying memory from the GPU or to the CPU, perhaps in the last line of code over here. So this allows us to measure the time taken for each operation, and then we can spot the bottlenecks as they occur. So here are some of the results for LaneNet. On the left column we have floating point 16 models, and on the right we have FP32. The top row is the Jetson Nano and the bottom row is the Xavier NX. So the y-axis is common for both of these. They're both the same range, so you can compare these graphs directly. And what we see here is that the Xavier NX is quite a bit more powerful than the Nano, and it's able to finish the inference in a lot less time. And we can see that FP16 is actually faster than FP32 for both devices. It's about 20 to 30% faster when you're using FP16. And we can also see that batch size is quite clearly detrimental to performance, because copying to GPU takes more time if you have a larger batch of data, because that's more data which you need to transfer across the memory bus, and that is, I guess, linear almost, actually, the time taken to copy with respect to the batch size. The surprising thing in these graphs is that the inference is actually not affected much at all by the batch size, and for some reason batch size of 1 takes less time than batch size of 100 for the Jetson Nano, and this is over several iterations. So this is over 100 iterations of running this test. We actually find that for some reason batch size 100 does not actually affect the inference time itself, but a lot of time goes into copying data to and from the GPU and CPU. On the other hand, when we compare to the gaming laptop, these results can be directly compared, and we can see that the gaming laptop is much faster than both of the systems above, and we get much lower latencies for inference as well as copying times. So this is a comparison of all the devices for different batch sizes. I believe this is for the FP16 models. So what we can see here is that the blue color is for the RTX 2060, green is the Xavier NX, and red is the Jetson Nano. So inference, when it comes to inference time, the RTX 2060 is a clear winner across the board. It's a much more powerful GPU than the other two. The main, I guess, interesting thing in this graph over here is that the Xavier NX actually has much faster it's much faster at copying data from the GPU than the gaming laptop, as you can see in this graph over here, and this one as well. So we can see that the memory bus on the Xavier NX is actually quite fast, and it's good for copying data across the CPU and GPU. This could also be because the memory is actually shared among the CPU and GPU for the Xavier NX, which is not necessarily the case for the RTX 2060, because the GPU maintains its own memory over there. So that is, I guess, one striking difference. But in all other operations, we can see that the gaming laptop is quite a bit faster. Reshape array is actually not at all time consuming, because this is just flattening the array. So the main time basically goes into the copying and copying to and from when it comes to large batch sizes. So here's the inference performance for a single image. So this is how many frames per second you can expect to get when you're just inferring a single image. And this is where the speedups in using a TRT model actually become very apparent, because on the RTX 2060, if you are to use the TensorFlow model, you get an inference time of about 80 inferences per second. But once you've converted it to TRT, you can get nearly 300 frames per second, as you can see here, or 190 if you choose to use FP32. The Xavier is also quite good, at least in the power budget in which it operates. The performance is very respectable, both in FP32 and FP16. The OpenVINO results are actually Intel's library. So Intel has an OpenVINO library which is used for optimizing ML models for their own chips, and we can see there that the Xavier NX can be is actually quite a bit faster than using the Intel CPU. So the Intel CPU is expected to be slower, but we can see the Xavier NX is actually twice as fast, and it operates at a much lower power budget than the Intel CPU. So that is actually a good point in favor of using the TRT model in this case. The other thing which is interesting is that the Ultrabook's GPU, so the Ultrabook has a HD 520 GPU, which is not, it's a rather old integrated graphics unit at this point, but we can see that it's comparable to using a powerful CPU, like a 9th generation Intel i7 is comparable to using the HD 520 for this inference performance. And finally, we can see that the TRT files on the Nano are one of the slowest of the lot, and this performance here is roughly comparable to what you can get on the Intel CPU when it comes to the inference time. So I would guess that a good amount of time goes into memory copying, which is why the performance when using a GPU is slightly hindered, and the CPU can actually still achieve respectable performance because the copying time is much less. So some of the findings are that recasting NumPy arrays, in case you have an int array and you want to convert it to float, for example, it's very expensive and it can actually take much longer than all the other steps. So it's important to keep your NumPy arrays in the right position instead of having to recast them each time. Xavier to NX GPU to CPU transfers are quite fast, as I mentioned before. Inference time is independent of batch size, and power consumption is interesting because for the Xavier NX we recorded a power consumption of 13.8 watts and 6.2 watts for the Jetson Nano. But as we can see from here, that you get a lot better performance despite the higher power requirements. And the last point is that the GPU is fully utilized during inference, which means the GPU is used to 100% of its capacity. So the Jetson Nano actually runs out of RAM for the 100 batch size FP32 benchmark. That's because it only has 4 GB of memory, and because you need to use a larger swap partition, that makes the GPU transfers a bit slower. FP16 is consistently faster than FP32, and OpenVINO makes Intel CPUs competitive with the Jetson GPUs, but it requires more power. So here are some of the issues which can happen when you're using TensorRT. So this is the source image over here, and this on the left is the binary mask of the neural network output. So this indicates the lanes as a binary mask, and this at the bottom is for the TensorRT. The one for the top is TensorFlow, and then after post-processing we get the lanes. And we can see that the TensorFlow model is able to detect 5 lanes over here. So we get 5 lanes here, but TensorRT can only detect 3 lanes. And that is probably because of the way this has been generated. The output binary mask has some inconsistencies from the TensorFlow model, and that results in less lanes being detected. So that could be an issue, and it would probably require some more tuning and post-processing to get this kind of result where we see 5 lanes are detected in the image. The other test was using CenterNet. So CenterNet is actually an object detection network, and it can be used to generate bounding boxes for objects in the COCO dataset. So this actually uses some of the scripts which are provided. So over here we can compare the TensorRT result with the PyTorch result on the RTX 2060. So the main takeaway from here is that the results are very good, very comparable for the TensorRT model. There's very little drop in MAP. MAP is like can be thought of as like the accuracy of bounding box detection across various metrics. And we can see that the results are basically identical, and the loss in detection performance is quite minimal. The difference is that we get much faster inference times for the TRT model. It's nearly twice as fast on the RTX 2060. This is for the Xavier NX. This is comparing 2 things. One is the 512 by 512 models. So 512 by 512 is the input resolution of the image, and 416 by 416 is another one. So we can see there's a bit of accuracy loss when you use 416 by 416. That is because the smaller image will have less details, which reduces the accuracy. And we get 84 milliseconds per frame, whereas we get 15 milliseconds per frame for the RTX 2060 for the same network. So the difference is quite considerable in this case. And when we compare it to the Nano cannot even run the 512 by 512 network, which requires this big image for the input. It can only run 416 by 416, and in that case we can see that it takes 360 milliseconds per frame, whereas the Xavier NX is doing it in 60 milliseconds. So nearly a 6 times speed up in that case. And the main thing which we can notice is that converting to TensorRT for different boards does not affect the inference performance. Like the inference performance of the Xavier NX at 416 by 416 is quite similar to the Nano at 416 by 416. So those are some of my findings when it comes to benchmarking these ML systems. There are several other things we can also try, such as trying out other systems and seeing their results, like their accuracy when it comes to detecting lanes, or to the MAP when it comes to CenterNet. And with that, I would like to conclude my presentation. Thank you.